La zone de l'UM6P est équipée d'un plan d'évacuation qui indique les sorties de secours et les gestes à tenir en cas d'urgence. Prenez votre temps de l'observer ou demandez de l'accompagnement par le staff organisateur de l'événement. En cas d'écoute d'alarme, prendre du temps, ne pas se précipiter, suivre les équipiers d'évacuation ou le chemin le plus proche vers une sortie de secours indiquée par cette signalétique. Ne pas utiliser l'ascenseur. Une fois dehors, se déplacer vers le point de rassemblement pour confirmer votre sécurité au responsable d'évacuation et ne pas quitter le point de rassemblement qu'après autorisation. Si vous êtes le premier à notifier une situation d'urgence au sein des lieux de l'événement, vous devez activer le système d'alarme en poussant sur les déclencheurs manuels. Nos équipes sont à votre disposition et vous souhaitent un excellent événement.
All right, hello, UM6P community. How are we feeling this morning? Welcome back to day 2. Let's bring some energy back to this room. It is so good to see you. Hello, everyone, and welcome back to Science Week 2024. This is day 2. If you've just joined us this morning, welcome. My name is Manal Bernousi. I'll be your host, your MC, your friend over the next few days. Team, if we could just put the music down, please, and we'll get this started. Thank you so much. Yesterday, we've had an amazing start to this week. We opened up with the official ceremony. We've heard from Professor Raphaël Yogier about the theme of transitions, which, as you all know, is our main theme for this year. We then moved to one of the most important transitions, I must say, which is the transition of our mind and mindset, with an exceptional talk from Professor Daniel Dennett. That was absolutely incredible. We then moved to material transition with crystal engineering from Professor Mike Zaborodko, and then we took it to climate and energy transition, which you all loved. So that was day one, absolutely amazing. Today is a really, really exciting day, and so make sure you plan to spend the full day with us here. We've got an amazing lineup of speakers here available for you, and it's an incredible opportunity really to interact and exchange views, so make sure you make the most out of it. I want to remind everyone that there is a fun challenge going on, right? Make sure you have your app, your campus app. So each time one of you, interacts, asks questions, each time you're just playing full out and making the most out of this experience, you're earning points. And the top performers actually will have 2 invitations to the best restaurants, I must say, the gastronomic restaurant here, which, believe me, I've had the privilege to try, and you really do not want to miss out on that one. So make sure you play full out, grab your phone, pull it out, download the campus app, and each time you're interacting, asking questions, you're actually earning points. So that's just a reminder for you, and I want us to acknowledge 3 students who have really been playing that game, and they've been really here and interacting, asking questions. So I'd like us to give it up for Ayman, Hisham Haboub, and Salah Hamzawi. Let's give them a round of applause. Let's bring this energy back to this room. Congratulations to you guys. You've granted this opportunity. And ladies in the room, I want us to shake up this top 3 tomorrow morning. I want to see more of you tomorrow morning on the top 3, okay? All right, so this morning we're going to kick off the day with something that truly, truly sparks our sense of pride. As you all know, Moroccans are excelling in laboratories around the world, and among them, 8 young researchers are working in the field of artificial intelligence. You'll get to hear from them in just a few minutes. This afternoon, we'll have a whole session about extraterrestrial life, aliens. So make sure you're here. It's going to be an amazing session by Avi Loeb himself, a one-in-a-lifetime opportunity. So really don't miss out, and be sure to be back here on time at 2 p.m. sharp. He'll be connecting from Boston. It's going to be bright and early for him, 8 a.m. So we really want to bring that energy back to the room and make sure we kick off on time. Then we'll talk about that transition to the digital education, which is a major transition going on, as you know, and we'll wrap up the day with a very special workshop. I've had the opportunity yesterday evening to talk with the facilitators, and it's a really amazing workshop. They're going to call on, people to come on stage and do a little experience with them, and it's about navigating transition in our own lives. That liminal space, the messy middle, when you know what you've left before, but you're not sure yet what is coming after. That's what we'll be working on, and we really want to be fully equipped for these life situations. So be sure to be with us here by the end of the day to get this experience and with the Center for Public Impact. And at 5 p.m., and I'm going to wrap up with that, we've moved up the schedule for you to free your evening. We'll have our very own private session, our very own private screening of a documentary, which is, a world premiere by Luc Hardy on this beautiful screen right behind me. So I want to see a full room, and we're all going to watch the screening, which is a world premiere. Again, this whole week has been really designed for you guys, so please make sure you're making the most out of it. I'm just blown away by the lineup of speakers that we have and the opportunity we get to interact with them. So I just want to make sure that we're all making the most out of it. All right, let's dive in now. For our first session, I'd like us to welcome our first speaker, who actually ranks up in the top 2% of researchers globally in science. He has authored numerous articles and publications delving into the digital technology broadly and specifically within the realm of AI. As a professor at École Polytechnique Fédérale de Lausanne, he leads the Committee for Teachers Promotion. He also chairs the steering committee for the College of Computing here at UM6P. Please give it up for Professor Rachid Gerraoui. Let's welcome him up on stage. Professor Gerraoui, welcome. It is, yes, let's please take a mic. Let's make sure it is on. It is such a pleasure to have you with us here today. I want to start with a couple of questions with you, if you don't mind, and then we'll get this started. First question may be a basic one, but let's start with basics. How would you define artificial intelligence for us?
Okay, tough question. Good morning, everyone. What is AI? And the definition I'm going to share with you is the definition by Alan Turing. AI is the ability of an algorithm executing on a machine to solve a problem that humans thought only they could solve. Are you with me? So at some point in history, humans believe that only they could solve a problem. And then an algorithm comes and solves that problem, so humans get surprised and they say, oh, this is intelligence, but this is artificial intelligence. What is important to remember, to notice, is that the techniques underlying these algorithms change over time. So the notion of AI changed over time. What used to be called AI in the 80s is not what used to be called in the 90s, and so forth. There are two key people underlying this definition. Alan Turing, I just mentioned him, he invented the notion of a machine as we know it today, and Al-Khwarizmi, who defined the notion of algorithms. So the two heroes, although Fouad Al-Arwi didn't mention them yesterday, Al-Khwarizmi and Turing are, in my opinion, the most important people in science nowadays. They are like Regragui or Ammouta. These are the top heroes of our times.
Amazing. Well, thank you for that definition. My understanding is that this morning we're going to hear from 8 young researchers. Can you tell us more about, how you selected these researchers?
Thank you for this question. We were asked to invite people to talk to you about AI. Of course, the tradition is to invite, I apologize, allergies, to invite dinosaurs. We have a lot of respect for dinosaurs. They are extremely important. I would like to be a dinosaur one day. I will be remembered. I would like these students to become dinosaurs. But we decided to invite rather the young generation that is actually pushing the frontiers of AI. And you have essentially 2 categories of people pushing the frontiers of AI. Those creating startups and companies, and those doing science. And what it means to do science is to publish papers. And the metric in AI as we know it today is a couple of conferences. One of them is called NeurIPS, and this is a clear metric. Once you get a paper there, it means when you get your result published in that conference, then you qualify as someone who is pushing the frontiers of AI. When we talk about football, there is the Mondial, there is the CAN, these are clear metrics. When we talk about tennis, there are clear metrics, Wimbledon, Roland Garros, etc. And we are very lucky in Morocco to have 8 young people who managed to publish their papers in this top conference. And believe me, this is not easy. It takes a lot of time, a lot of stress, a lot of motivation, and I'm extremely happy to have them today.
This is amazing, and we very much look forward to learn more. The floor is all yours, Professor. Thank you so much again.
Thank you. So before calling them, at least one of them, to start, let me tell you that it's not easy for them to come. They are all extremely busy. They are finishing their PhDs, doing something else, interviewing here and there, but they all said immediately yes, and I think this is, I would like to thank them for that. And I would also like to invite the students in this room to try to project themselves in few years, and hopefully some of them will manage to have papers in these big conferences. So this is really a clear goal to have, something very prestigious. Before inviting them, let me thank people who have made this event possible. Of course, Saad, Hisham, Fuad, and many others. And this is a day organized by the College of Computing, which is a very prestigious college at UM6P. And I would like those in the college who have helped organize this, I would like to thank them. And there will be a special event with them this afternoon. And some of the students of the college will also present their achievements, which I believe is extremely promising. So I will start by calling Nehale. Please join me on the... So they will have each 10 minutes to present their work. And I try to interact with them to convince them not to have too much mathematics in their slides. We'll see whether this is gonna work. And the students of the College of Computing, please raise your hands. Please pay attention to what's going on. You will be asked to record videos summarizing what they are going to say. No pressure. So please try to pay attention, try to understand what's going on. The first speaker is Nehale, and believe me, I didn't do it on purpose. Bint Tasfi.
Thank you. Good morning, everyone. So first, I'm wondering if there is a... Ok, mais c'est pas grave, c'est pas la peine. Ça marche. Okay. Good morning, everyone. I'm very happy to be here with you today. And I'm going to tell you a little bit about my general interest and some ongoing research. So before that, okay. So before that, I'm going to tell you a little bit about myself, my personal journey. So I'm from Mohammedia, where I did my high schools there and obtained a baccalaureate in mathematics. And after that, I did what we all know here as classe préparatoire, which is these 2 very intense years in math and physics. And it's very hard for me to be here because I did my first year in this very same campus when it was just starting to be built. Yeah, and after that, I went to an engineering school in France called Centrale Supélec, where it was an engineering school, but I was specializing in mathematics and data science. And it was 4 years where I had time to do other things on the side, some other extracurriculum activities. And in parallel of my last year in Centrale, I was in the ENS Paris-Saclay, where I did a master's related to AI, vision, and machine learning. Yeah, and after that, I was very lucky to have an internship opportunity in the Montreal Institute of Artificial Intelligence, where I was supervised by 2 amazing people, and it led to a PhD offer, which I am on still until now. So here I am today. Okay, so let's dive into the actual subject. So what if AI could help us to discover new drugs? What if it could really actually change the way that practitioners discover new drugs today? And I want to tell you a little bit first about proteins, which are the building blocks of life and of also drug design. And in practice, for practitioners, in order to make these drugs, it takes a lot of time and it costs a lot of money for them to do this. So there is a natural question that arises. If we have enough data, and if we have enough data and enough information about these proteins, can we try to accelerate this process? And there is a lot of ways to do this. One way is to use actually the 3D structure of the protein. Why? Because for practitioners, if they look at how the protein folds and shape in space, it's going to be easier for them to determine its function, whether or not it's going to be able to kill a virus, whether or not it's going to have side effects on the human body. So really having this 3D structure of a protein allows us to have much more information than just looking at the sequence of the atoms that constitute this protein. But the thing is that this 3D structure prediction is a very, very, very complex task. And there is some kind of world championship just for that, where we have more than 100 research labs which are going to compete to try to predict the 3D structures of many proteins to the best accuracy possible. And 2 years ago, a team from DeepMind was able to solve this problem almost really incredibly well, with an accuracy of something like 90%. And it was with a model called AlphaFold 2. And it was really a breakthrough, and right now it's being used by practitioners everywhere in the world. So that's it, problem solved, but not really actually, because AlphaFold 2 has been amazing, but it has one major drawback, is that it predicts only one 3D structure for each protein. But is that really the case? Is that really how proteins work? Well, not really, because they move and they fold in space, and they are dynamical, so they change shape all the time. So if you can see here in the third figure, we have the same protein, but it changes shape on an energy surface, and it can take different forms. And so the question is, can we, instead of predicting just the most stable structure, so the one with the lowest internal energy, can we try to predict to find all of these different modes, all of these different diverse 3D structures that this protein can take? So it's a little bit of an exploration problem, but also an exploitation problem. We want to find the best structures that are diverse also. And so this is what I'm working on for my PhD. Okay, so now we're going to dive in a little bit more in the technicalities. How can we tackle this problem? So suppose that we have some oracle that when you give it the 3D structure of a protein, it gives you its internal energy. So it tells you how good this protein is. The lower this internal energy, the more stable the protein is going to be. And one very successful way of doing this that has been tried in other places is to do it this way. So we start with a random structure of our protein. So at the beginning, it's just, let's say, at the beginning, it's really just garbage. It's this S0 code here. And then we consider that our protein is made of many small fragments. And the idea is that we are going to orient them in space. So we're going to do some rotations and some translations of these fragments. And it's going to be, at each time step here, tiny rotations and translations. And in the end, we're going to obtain a generated structure. And these orientation in space are going to be learned with a neural network that here I refer to as P theta. And at the beginning, this neural network doesn't really know what it's doing, but then it's going to learn with a reward function. And its reward is basically just the energy of the generated structure. And we obtain the energy with the oracle. So you can see this oracle a bit like a teacher for the neural network. The neural network is going to generate a structure, and then the oracle tells it, oh, okay, this is very good, you should keep generating things that are similar. Or it's going to tell it, oh, no, this is bad, And so the difference with AlphaFold is that here we want to learn this P theta such that we're going to be able to sample proportionally to a quantity which is the exponent, which is like a function of the energy, and the lowest the energy, the higher the probability of sampling. So you can see here we have the energy of our final structure, Sn, and the lower the energy, the higher we want the probability of sampling to be. And for AlphaFold, there wasn't this proportional side. It was just trying to maximize for the lowest energy structure. So you can see this trade-off between exploitation, where we want to find the best structures, and exploration, where we want to find diverse structures. And this problem is really, really hard for big proteins because the space of search is just really big. Like imagine having something like 10,000 fragments and you want to move them all in space. So it gives you a lot of different, like an infinite search space. And this is really the difficulty of this problem. Yeah. Sorry. Yeah, and I'm not going to dive in a lot in the technical details of this, but just to give you some keywords, people use things like diffusion models or variational inference to solve for these problems. And there is also a new framework that has been developed in our lab called GFlowNets, which I think one of the speakers is going to talk about after, which also tries to solve for this very same problem. So this is still very much ongoing work, it's still baby work, and we hope to have results on this very soon. Okay, so there is still a lot of open challenges in this field. It's actually really, really exciting, and there is so much to discover and to try to unravel. And I'm going to give you two examples of open challenges. The first one is, what if we don't have access to this oracle that I told you? You give it this 3D structure, and it tells you whether or not it is good. And actually, we don't know this oracle for the big proteins, because if you want to obtain the internal energy of a protein, you need to do some quantum calculations. And the quantum calculation means that you are going to look at the electrons that constitute your protein. So basically, doing this calculation scales quadratically with the number of electrons that you have in a protein. So the bigger it is, the harder it is. And this is still an unsolved problem. Okay, I think do I still have a minute? Or? Less than a minute, okay. And yeah, the second challenge is, can we use this framework that we talked about before to actually try to design the protein sequences for a specific target? And I don't think I have time to talk about the methodology, but yeah, that's mostly it. Thank you so much.
Super. That was not an easy exercise. In 10 minutes, say what you are doing with maximum 1 slide of mathematics. That was the deal. For those of you who have questions, please keep them at the end of the first session. There will be 4 talks. If you have questions, we will open the floor for questions. Next speaker will also talk about applications of machine learning to other topics, solar radiance. Please, Ghait, the floor is yours.
Yeah, I can start right now. So it's a great pleasure, it's a great honor to be here in front of you. So right now I'm going to discuss a very interesting intersection between machine learning and the renewable energy, specifically focusing on solar radiance forecasting. So I'm Ghait Boukachab. I'm originated from Inzgan. It's a city just, it's kind of famous. It's a city just, yeah. It's next to Agadir. So, and right now I'm a data scientist at Venus Analytics and visionary researcher at Milan. So let's embark with my personal journey. So I did my foundational studies at Lycée Technical Idrissi in mechanical sciences and technologies. And progressing to CPGE, to industrial sciences and technologies at Lena Nehale at Agadir also. And in 2017, I started my journey in industrial engineering. So it was there with, where I discovered, where I specialized with machine learning. But first, as a decision-making tool, it's like replacement research, it's like game theories. It was not my plain focus. And I did my internships here in Morocco. After that, to dive in and to go deeper in this field, so I pursued my master's at Université Québécoise Rimouski, and I also joined in Mila with the supervisory care of Lena Nehale and Youssef Allouah, where I worked on my research project. And after that, I also served as a teaching assistant for many courses there. So with Aaron Corvi for presentation learning, and with Guillaume Arbissot and Yanis Mitigriagas for foundation of machine learning. And I became also a member of Gerard and Cyril. So Gerard is a group for research of decision analysis, and Cyril is Inter-University Center for Logistics and Transportation. And and I graduated last year, and right now I'm continuing my collaborations at Mila as a visiting researcher, and I'm also a data scientist at Evidence Analytics. It's a startup also with Mila. And so let's directly dive in why I'm here. So this is I'm here to discuss our last notice paper. It's called it's named Improved Solar Radiance Forecasting for forecasting. So right now, why we should forecast solar radiance? So yeah, if we have a great forecast, if we have a precise forecast, it should be they're gonna help us. They're going to help managers of energy to better plan their production, so to know how they should inject in the grid, how to if they want to produce or not. So what we would like to do, so we would like to forecast solar radiance within a useful horizon, so for a few hours to 1 day. For every point of interest in the world. So and we have a problem. So long-term solar radiance forecasting is a little bit of hard. So why was it hard? So we have two kind of GHI, so solar radiance forecasting. We have some kind of low frequencies. They are solar radiance, so they are easy to estimate. They are just regular. It's like a clear sky model. And we have high frequencies where we have some stochastics and some stochasticity. It's generally due to random process like clouds, like aerosol, etc. And so, what if we just use time series? Time series are not. We don't have that kind of information about stochasticity in that time series. And even if we use the most state-of-the-art deep learning models, they are not. We have a promotional result, but they are not. It just help us to predict low frequencies components, not high frequencies components. So we decided to inject some spatial temporal context around the station to help time series model to get the useful information for them. So, but how we did this? So right now I'm going to introduce our main contribution across Vivit. So so we design an architecture. So it's a multi-model machine learning architecture. So the two modalities that we have here, we have satellite images around the station. It's OMETSAT satellite images. We have some we have infrared, we have visual and aerosol channels, and we have also some time series data. So there are just some historical observation in some ground station, and we are trying to mix the two modalities. So for the first one, separately, for the first one, we use the vision transformer after tokenizing and masking. We use the masking to avoid overfitting and some regularization, and also for the time series. And we use a atom transformer, and after that we try to mix them in a cross transformer. And we have and we use artificial position encoding to give the information to the model where to look in the satellite images to get the exact information from that's going to help the time series. And we have two versions. We have one version that gives deterministic forecast. And the version that we showed here in the architecture, so it gives probabilistic forecast. How we did this? So we're trying to predict every quantile in the prediction, and we have some results like some prediction like this. And I'm inviting you to check our GitHub repo. We have some great visualization and also the paper to get more information about it. So that's it. So for what I'm currently working on. So right now, CrossVivid is a architecture that specialized. Originally specialized for time series forecasting. So what if we try to improve this architecture to use it for any physical variable? So this is what we are working on right now. So we're trying to expand the architecture for various for various variables. And we are also trying to advance towards solving partial differential equations. So for example, we have Navier-Stokes frames. We are trying to predict next frames, so something like this. And I'm working with Oussama Boussif, who's gonna be the next speaker, and then Sulin and some other authors. And also, as an industrial engineer, I'm trying to bridge the gap between what is called engineering field and machine learning. So because there is a huge disconnection between them. So we have. For example, I'm working currently with Salem Lahlou on implementing machine learning algorithms for logistics, maritime logistics. So our goal is to enhance efficiency and the innovation in maritime logistics through AI. So by predicting for example. We published a recent paper to predict the quality of using the control quality chart and the machine learning algorithm to predict the estimated time of arrival. So that's it. Thank you.
Okay, while calling Oussama, I don't know if you noticed, but Ghait has put the list of authors of his last paper on the slide, and 4 of them are from Morocco. And I would like to thank Professor Ben Abou, who has been educating many students in Canada. Les Marocains du monde, even in Canada, they're really educating the young generation. Oussama, the floor is yours. 10 minutes, one slide of mathematics.
Perfect.
Maximum.
Yeah. So thank you very much for having me. It's really a pleasure to be here. It's also a really special place for me because I was here 8 years ago, where I spent a year studying at LIDEX. So before that, I started my baccalaureate in Lycée Ihsan at El Jadida, so I lived in El Jadida. And it was kind of a special year for me because I had the opportunity to participate in the Physics Olympiad and also at the general competition for science and technologies. And next to that, after that, I went to LIDEX, who all of you are familiar with, and I was also lucky to be among the first cohort. And as I said, it's a really special moment for me here because I've spent a year in this very campus, and I can also see how much it changed since then. And I'm really happy to have a university of this caliber in Morocco. And after that, much like Lena, I did my engineering studies at Centrale Supélec, where I studied applied math and data science. And normally it's only 3 years, but you can see here it's 4 years because I did a gap year. And apart from another internship, I also went with a brass band to give musical workshops to children in Mozambique and Togo. And after that, I did my last year's master's in parallel at l'École Normale Supérieure. It's at the MVA Masters, so Mathematics, Visions, and Learning. And after that, for my end-of-year internship at Centrale and ENS, I went to Mila, where I was supervised by Professor Yoshua Benjio to work on AI for advancing scientific discoveries, and where I had the opportunity to get 2 first author papers at NURBS and ICLR, one of which I'm going to present next. And in 2023, I started my PhD with Yoshua on the subject of AI for scientific discovery. So, although my subject was in AI for scientific discovery, I started with the first application of weather forecasting, which is what I'm going to talk about now. And why do we care actually about simulating the weather and forecasting it? By the way, these images are courtesy of ChatGPT, so I'm going to give credit where it's due. So the first aspect is climate change. So you all are aware of this problem. Yesterday, there have been some talks on that. So we want to predict its impact and devise mitigation strategies. And forecasting the weather can give us kind of an informed way of doing so. There's also the disaster preparedness problem. So hurricanes, wildfires, if we are able to predict that and forecast that, some days in advance, then we can devise early warning systems and mitigate the effects of these natural disasters. And the last cornerstone is also tied to climate change, which is the supporting renewable energy. So you saw Ghait presenting our work on forecasting solar irradiance that would help better manage the solar power plants. So it's good for efficient deployment of renewable energy, but also optimizing energy production and distribution. Now, we talked about why it's important, now how to simulate the weather. So traditionally, weather forecasting systems are actually just what's called partial differential equations. These are equations that can evolve in space and time. And weather dynamics in particular can be simulated using these partial differential equations. Now, the problem is you have to solve them. And you can't, at least for weather, you cannot solve them analytically, which means that you cannot have a formula saying, okay, this is the solution. And so what we usually do is we numerically solve them. So you plug the equation into a computer and you just run the algorithm to solve the PDEs, and you hope for the best. The problem is it's very expensive. Now we have large supercomputers that can generate weather predictions, and that's how you get the weather predictions on your phone, like the temperature and the wind and so on and so forth. But it takes huge clusters and a lot of computing power to do so. And so the hope with machine learning is to speed partial differential equation solving, but in a way that can be also generalizable, so we don't have to rerun these expensive processes each time. And this is where our work on solving PDEs, partial differential equations, comes into the picture. So this was a work done while I was an intern. It's a work that appeared at NeurIPS 2022. And the paper called Mesh Agnostic Null PD Solvers, or Magnet for short. So the point of this model is to be able to predict the partial differential equation solution at any point in space. So I said that it takes a lot of time to solve them numerically, and what we want is a model that can be trained once and then deployed whenever we want, so that we can get predictions in matter of seconds instead of hours on thousands of CPUs. So this work aims to bridge this gap, and the whole, I guess, point of it is to be able to do what's called super resolution. So that means that if I give, I ask the model, okay, what's the temperature at, Benguerir, then without having been trained on that specific position, I should be able to get the prediction accurately. And also another highlight is that it works on the regular and irregular grids, which means that the points do not have to be placed uniformly at a uniform distance from each other. And so how it works, briefly, I didn't have really mathematical slides because otherwise it's going to be a bit more dense, but we ask the model to say, okay, at this time you're going to receive positions for which you have to predict the weather that you have not seen. So let's train you to do this task so you're not surprised at deployment. So we divide the grid in two parts, the parent mesh and the spatial queries. At the spatial queries, we only have the positions. You don't know what's the temperature or the wind speed or whatever. And what we ask from the model is that you give us these values at the spatial queries. But at the parent mesh, we already know what's the temperature or the physical variables of interest. And these spatial queries will go through this interpolation module. You don't have to dive into the details, but what it basically does is that it's going to predict the solution at these spatial queries, and then through a loss function, or what Lena called the reward function, the model is going to be, okay, if you get this prediction right, then don't change your parameters, otherwise tweak your parameters so that your model get the predictions correctly. And what we observe is that you can actually generalize from just a small number of points. So one of the highlights of the paper is that we gave, I think, about 1,000 sensor measurements during training. That's all the model ever saw, and it was able to generalize to about 64,000 new points. So that's the highlight of super resolution, and it's really especially relevant for weather forecasting because we don't have a lot of sensors spaced everywhere. Plus, they're not placed at regular grids. They are on an irregular grid. So it means that it can generalize from seeing just measurements from a few points. And as a future work, we hope to extend this framework to also temporal super resolution. So I said that the model has not seen the solution at some points in space, but what if we also have missing points in time? We also would like to forecast them. And we can also enhance the interpolation module to make it work better. And also maybe use clever sampling techniques. So as I said, the sensors are not always placed in a regular grid. They're all sometimes condensed in one point. So we'd like to adapt the sampling to adapt for these special cases. And maybe also apply the model to more challenging tasks. So the model that I presented was just put on partial differential equations, simple ones. But if we can apply this to weather, then it's gonna be better even. And yeah, that's it for me. And thanks a lot for following the talk.
Okay, so as I pointed out earlier, if you have questions, you might be able to ask them at the end of the next talk. Otherwise, you will meet them during the break session and you can ask more questions. You don't need to ask questions, but if you have some, we might take them at the end of this talk before the break. Next speaker is Ziyad. Thank you again.
Thank you. You hear me good? Okay. So hello everyone. I am Ziyad Benomar. and I will be talking to you about online decision making. So first, I would just like to thank again the organizing committee and also Professor Rachid Gerraoui for the invitation. Sorry. Yes. So it's my first time at the campus of UM6P, and I'm very happy to be here. So very briefly, I am from Rabat. I was in Al-Madaris Al-Hassaniya for my baccalaureate, then I went to classe préparatoire Ibn Ghazi. Following that, I went to École Polytechnique in France, where I majored in computer science and optimization. Then I did a research-oriented master's degree in the theory of machine learning, and since October 2022, I am a PhD student in a joint laboratory between ENSAIA and École Polytechnique under the supervision of Professor Vianney-Percher. So regarding my research, very broadly, I'm interested in online algorithms, and this includes online learning, namely bandits problems and reinforcement learning. I am also interested in online algorithms, which is a subfield of theoretical computer science. And my current research focus is online algorithms with predictions, also referred to as learning augmented algorithms. So in the setting of online algorithms, what happens is that the decision maker observes the input sequentially, and it does not observe the whole input at the beginning, but it observes it sequentially during time. And at each new step, the decision maker must make a new decision. The problem is that the decision maker ignores the future and must make decisions that will guarantee a good reward by the end, even the future is unknown and can be adversarial, which means that we must make decisions that are robust in face of the worst possible future. So due to the inherent difficulty of such problems, there is not much that we can do. So there are algorithms, but their performance stays limited. So in today's context, with the rise of artificial intelligence, it is reasonable to assume having a prediction on what will happen in the future. The only problem is that we don't have much guarantees about these predictions. So in general, in theory, when we work on machine learning, we demonstrate that the predictions are good in expectation or good with very high probability, but it does not guarantee that in my particular case, when I want to make a decision, the prediction is good. So the next question is how to leverage the predictions to make the best action possible, knowing that they might be not accurate. So this is not an easy question. In fact, it is very complicated. And to convince you, I'm going to present a very simple problem, which is the ski rental problem. Imagine that you are living in a city where it snows from time to time, let's say Ifrane, for example, and imagine that you really want to ski every single day when it's going to snow, okay? And imagine, for instance, that at each new snowing day, you can either rent a ski for the day for 10 dirhams. I know it's very cheap, but yeah, let's assume. And yeah, you can either rent a ski for 10 dirhams, or you can pay the annual subscription for 200 dirhams and not have to rent after that. Okay? So the decision depends on, the optimal decision depends on the number of days when it will snow. So imagine you have an artificial intelligence telling you that it will snow for 17 days during the year. So if the prediction is made, for example, by Oussama or Ghait, I would trust it, but otherwise, I don't have much guarantees on the prediction. So without any guarantees on the quality of the predictions, how to make an algorithm that is both consistent, which means the algorithm must perform very good if the prediction is accurate, and in the same time, the algorithm must stay robust in case of incorrect predictions. So yeah, just before moving to the next slide, this very simple problem, with the ski rental problem, exactly as I introduced this right now, was first presented in 2018 in a paper in RIPS. And until today, there is still no optimal algorithm known for this problem, for this very single problem. So there are good algorithms, but not optimal. So if any of you might have enlightening ideas regarding how to do this, I would like to discuss it with you after that. Regarding what I work on, I am mainly interested in settings where we have a lot of predictions, a lot of unknown variables, and a lot of predictions. And what I'm trying to study is how we can improve the performance with respect to the number of predictions that are available. So the paper that was accepted in the RIFs is about a setting where the decision maker can query the predictions at the times that he wants. So imagine you have multiple days when you must make decisions, but you can query, let's say, 3 predictions. And this corresponds to settings where the predictions comes from an expert, and it is costly to obtain them. So you just have a limited budget, and you must use it sparsely in an intelligent way. And then I also have another paper that I worked on currently, which is the one I want to talk about a little. It's about non-clairvoyant scheduling with partial predictions. So it's still a submitted paper. We'll see if it gets accepted. But in the paper, we work on the scheduling problem, which is motivated by implementation of operating systems, for example. And we provide an algorithm that has a competitive ratio. So the competitive ratio is the metric for measuring the quality of online algorithms. We have a competitive ratio of 2 minus b over n. So yeah, I think to fully explain what the competitive ratio is and why the 2 minus b over n, it would take some time. So just accept that I have a competitive ratio of 2 minus b over n when I have b predictions, and we proved that no algorithm can do better than 2 minus b over n minus 0.04. So it's an almost optimal algorithm. And we also studied the case of imperfect predictions. So in that case, the algorithm needs to be randomized to guarantee certain properties, and it also reveals some very interesting behavior when we have limited number of predictions. So compared to the case where we have full predictions. So yes, we think it is a paper with a lot of potential, and I would be very happy to discuss it with anyone after this presentation if you are interested. So other than that, I also work on online selection problems where you observe candidates. Let's say you are in an HR department and you are interviewing candidates one after the other, and with each new candidate, you must decide to either reject them or accept them. So the problem is that you want to accept the best candidates overall, and mainly this is modeled as variants of the secretary problem or the profit inequality problem. And I'm interested particularly in settings where we try to close the gap a little bit between the theory and real applications, because the basic problems represent very, very simple cases. So final remarks, what I would like you to retain from this presentation is that learning augmented algorithms ask the question of how to efficiently use AI. Okay, so we have AI. Now how to use it in a good way to make the best actions. Next, it is a field at the intersection of algorithm design and machine learning. So there are lots of open questions and a lot of research directions that might interest both people from the ML community and also from the computer science community. So some interesting research directions are how to quantify optimal algorithms. There are some definitions, but there is still not a very good consensus of what is a good algorithm. Yes, we can use, in ML algorithms, we often train an artificial intelligence using a loss function, saying this is the quantity we want to minimize. So what if we use the objective of the decision-making problem as a loss function? And there are a few papers who do this, and it proved to be quite good. So yes, it is a very promising research direction. Finally, the very common applications for learning augmented algorithms are in the design and implementation of data structures. And there are also some papers that try to apply this paradigm to machine learning algorithms. So we start in a learning problem, and we assume that we have some predictions of what is the good Q table, for example, in reinforcement learning, or what is a good classification in a classification problem, and starting with a noisy prediction, how to deliver a better prediction by the end. So that was it for me. Thank you for attending this presentation.
So we have some time for questions, if any. If you decide to ask a question, I think you can raise your hand, you will get a microphone. Please mention to whom the question is addressed, or you can say that the question is general. And then I will call the corresponding speaker. I see that there is a hand raised there. I don't know if somebody can bring microphones to the... So while the microphones are circulating, okay, there are a few questions. So please make your question very precise. And the point of the question is to give something to say to the speaker, not to talk about yourself. The microphone, please. There is a gentleman over there. Thank you. So the rule of the question is to whom the question is addressed, and please try to be concise, and I will try to call the people or have them.
This question is to Lena.
To Lena. So please, Lena, come. Thank you. You can go on with your question.
My question is that you mentioned reward function when you are presenting. I would like to know if the type of deep neural network used is reinforcement learning, and about the reward function, are you the one to design the reward function, the initial reward function that the system is going to learn from initially before it starts adjusting itself?
Okay, so I didn't get the second part of your question, but I can answer the first one if you want, just about RL.
So I said the reward function, are you the one to design the reward function initially before it starts adjusting itself subsequently?
Okay, so for your first point, so what we're doing is not really RL, because RL is trying to maximize the reward, right? But in our case, we are trying to sample proportionally to the reward. So it's exactly the difference between what AlphaFold does and what we are trying to do here. So AlphaFold tries to find the only structure that is going to maximize the reward function, just like RL. But here we want to sample proportionally to a distribution. So it's not really like RL. And for your second question, the reward function is fixed at the beginning. So we already have it. We have an oracle that tells us how good is your structure.
Thank you.
Yeah.
Lena, stick around. I have a question for you.
So raise your hand first, or we see. Yes, please go ahead if you have a mic.
The mic also. My name is Rahil Kamar. I am from ISESCO. Lena, question for you again.
For Lena. So please, Lena, come again.
My question is that, you know, when you do ab initio modeling or you do homology modeling for protein structure, what you are assuming per se is that you arrive at an energy minimum. And you arrive at an overall energy minimum, especially when you're doing ab initio folding. But we know with a fact now that proteins do not fold, you know, overall, or do not, even in homology modeling. When you do homology modeling, if you look at the overall structure, you will arrive at a false structure. Proteins basically fold in domains. So each domain you energy minimize, and then you move on to the other domain, and then the overall energy minimization occurs. How does AlphaFold work? I'm not familiar with it. Does it do an ab initio folding or a homology folding? Or, and the second part of the question is that, you know, proteins are not static structures at all. They are dynamic structures. So the structure that you arrive at by ab initio folding or homology modeling folding might not be the real structure that the protein actually falls into.
Okay, so I am not sure I fully understood the first part of your question, but I can try to answer the second one, and then we can go back to the first one if you want. So I'm not 100% sure, but by what you mean when you're saying it's not exactly the case, it's not exactly the real structure. Do you mean that to obtain the exact structure we need to do quantum calculations, and what we are actually doing is just classical calculations, classical physics calculations? Because if this is the case, yes, in general, in molecular dynamics, we do like very a very, very relaxed assumption where we just ignore the quantum effects and we treat the protein just as we would treat a very big object, and we just do classical physics to predict its dynamics, but it's really not accurate, especially when you have a very big protein where you have electrons that are interacting one next to the other, and it's really these quantum effects that have the highest impact.
Yes,
And
then that is where the problem arises.
Yeah.
When you do ab initio folding, you do an overall energy minimization of the structure, which is not the right way to go about it. The right way to go about is look for domain structures and do energy minimization on them. And once the domains fold, and then you bring in the other domains and all that. So if you do an overall energy minimization, you might not arrive at a correct structure because domains are more important. That is what my first question was.
So I'm not sure what you mean by domains, but
Proteins
folding
have different domains. Na? For example, let's say if you don't go into tertiary structure domain, let's say alpha helix is a domain, let's say beta sheet is a domain, let's say random coil is a domain. So they will fold first with energy minimization and not just the protein snapping into structure.
Right, right. But the thing is that energy minimization and having a protein that folds is exactly the same, right? Because the protein that is folded has the lowest energy and it's the most stable. And if you have a protein that is unfolded, it's going to have a higher energy. And if you have like some clashes between the atoms because they're just too close to each other and it's not physically possible, you're going to have like a high spike in your energy. So energy gives you actually everything that you need to know about these domains. And energy contains the whole information about it.
Thank you. Thank you very much. Thank you, Lena, for standing up on this long question. More questions? I see somebody raising a hand over there. And then there are a couple, so we can take 2 or 3 more questions. And while the mic is circulating, some of you came late and might be asking themselves the question, what the hell is going on? What is going on is we are at the frontiers of AI, which is machine learning today, and we have invited top-notch Moroccan students who are pushing these frontiers by having their paper appearing at the best conference in the field. So for the latecomers, please go ahead.
Hello, my question is for Lena too.
So next questions should be for other people, please. So this one is for Lena, but please pick questions for the others as well.
I'm a biology student, and I know a little bit about molecular docking. So molecular docking is a software or things we do to pretend whether a drug is going to get a receptor and going to stick with it. Now, to do this, we need, as you said, a low energy, and we need a specific sequence to stick to the receptor. What I didn't get is if this manually steps, we do the protocol of molecular docking manually. So our your study is about AI to do these steps without follow it. Like for example, you don't follow the protocol. You just give the protein to the AI, and see whether it's going to stick to the receptor or not.
Yes, that's a good question. So actually, there is some neural networks that are able to do this docking for you, and they are called force fields. And they are neural networks that have been trained so that if you give it just a protein, or as you say, the protein and like a ligand that it wants to stick to it, it gives you the corresponding energy. So there is trained algorithms for that.
So from now we're going to use the algorithm to see whether it's going to stick, instead of doing all the chemotech and all the protocol.
Yes. What you mean by the protocol is to try to predict by hand whether or not these two things are going. Yes. So that's exactly the thing. So you have a force field that can do this for you, and if you think about it, it's really just like physical calculations. So you can do it on a computer, and then what remains is how precise are these calculations. So if your protein is small, it can be quite precise, but the bigger it is, the harder it is, and it's actually very, very, very approximate. But that's a good point.
Okay, thank you so much, because this is going to help us so much.
Yeah, and happy to discuss with anyone after that. So.
Yeah, thank you so much.
Any questions to the other folks? there is a hand raised there.
So hello everyone, thanks for the conference.
Speak close to the mic, please.
So my question is for Sir Ziyad Benomar for the fairness of online selection. The issue is when you have an internship interview or whatever interview you have, there is also a behavior interview. For the technical interview, we are not biased, for sure, but for the behavioral one, how the computer can get the data to analyze it and find the best competitors for the job or whatever we are interviewing for.
Okay, thank you very much for your question. I'm sorry to disappoint you, but this is not exactly what I'm working on. When I said that I worked on online selection with fairness, well, the exact problem we worked on is that we assume that we have candidates belonging to different groups. Let's say, for example, candidates coming from different universities. And when you have candidates belonging to the same university, you can more easily compare them because they studied the same courses, they have grades such as GPA and other metrics that facilitates the comparison of these two candidates. But when you have candidates belonging to different universities, it is not always easy to compare them. You must really go through very well-designed interview process. So this is a little bit your question. And I did not really took into consideration these particular aspects. But what we worked on is especially assessing where you have perfect predictions between, comparisons between candidates belonging to the same university, but noisy predictions between candidates belonging to different universities. And the idea is to try to select the best candidates overall, despite this difficulty in comparisons.
Any more questions? There was a hand raised over there. So the challenge is to make the question very short so that more people have time to ask questions.
So hello everyone. I'm sorry, again, my question is for Lena.
Okay.
So I'm a pharmacy student. I want to ask you, like you said that your model will generate different 3D structures for a specific protein. So my question is, like, how can you select for the right 3D structure that will perform a specific function, for example, inhibiting another protein or a target, or for example, binding to a receptor?
No, so that's the point. We don't select for the best protein because the truth is that it's. Oh, better? Okay. So that's the point. We don't select for the only best structure because the truth is that it's a dynamical system. It changes in time and it changes in space. So if you want to test how good is your protein compared to a specific target, you have to take into account all of the different ways that it can fold. And what we care about is an average quantity over all of this space of folding.
Thank you very much. Robert, there's a raise.
Thank you. I'm not sure, but it's the guy with GHI forecasting. It's Oussama.
Yes.
The name.
Weather
right?
forecasting, please come in. Yes, thanks, Robert. So before you ask your question, Robert used to be a student in Lebanon some time ago. He moved to France, then he moved to Germany. He was professor there. Now he's professor at UM6P. Thanks for being with us.
Thank you.
Now you can ask your question.
Yes. So in the market, there exists a lot of forecasters based on machine learning. Some of them are paid. Some of them are unpaid. Let's say open source. So my question is that how do you compare your methods with respect to those which already exist in the market from the accuracy perspective? One. And the second question is that is your method, when you say that it's very accurate, will be open source so that everybody can use it, or it's going to be like the others paid?
Yeah, to answer the first part of the question, so just our problem is we compare this with existing time series open source algorithms. So right now, because unfortunately, for example, in engineering papers, they are trying to predict something that is unpredictable. Predict 1 day ahead using time series without any information about the context is going to be very hard. So yeah, we compare it with the existing time series, baselines, and we use also some in the paper some Fourier, some persistence algorithms, some Fourier algorithms, but we didn't use that specific black box algorithms because we didn't have access to them. And for the second question, yeah, we have the code published. We have the data is published. Everything is on GitHub, so you can try it yourself. That's it. Yeah.
Any more question? Actually, before the mic goes there, I have a question for Oussama Boussif. How do you deal with poisonous data? Maybe you can come and answer the question. So the question is, he's working on weather prediction, and sometimes the data is bad, and the data can basically screw up the entire training. And my question to him, and I wanted him to come on stage, is to explain to us how he deals with poisonous data, bad data.
That's a good question. I'm not sure we do in the actual model, but I would suppose that if if some points are have a lot of noise, then you would hope that by correctly learning the process that it's gonna know how to avoid that. We also kind of play on the fact that we force the model to predict at points that it has never seen, so that can be called interpolation. And it does, I guess, a smoothing process there so that it gets the real value of the predictions. But I guess if we used a more, generative approach rather than a deterministic one, it should deal better with these poisonous data.
Maybe last question. There is one mic there.
Good morning, everyone, and thank you for the presentation. My name is Soumaïl Indeba Bienvenue. I'm a PhD student at UM6P and Green Energy Park on wind energy, and I am working on wind speed forecasting. So the question for Oussama is also more than outliers. How do you deal with some fluctuations that are related to variable governing the weather forecasting? Because there are some, for example, the direction of wind speed does not vary as much as wind speed, for example, or pressure or temperature. So how do you deal with those fluctuations in your algorithm? Thanks.
Yeah, just get close to the mic.
Okay, thank you for the question. So that's a good question. I think for variables that do not, that are easier to predict, it's maybe better to have a simpler, part of the model that predicts it, because you don't need that much capacity. But if it's simple enough, I guess a neural network should be able to predict it as well. So just feed everything you have to the model, and will be able to figure that out. I mean, that's my intuition. Otherwise, if you really have a simulator that does that better than a neural network, then just use that. For example, in Ghait talk, he talked about solar irradiance, and we have these baselines called persistence models. So what it does is just going to copy the past days, predictions, and just copy paste them into the next day. So it's just going to say, okay, the solar irradiance of yesterday is the same as today. Just copy paste. And in this case, at least for places where there are not much clouds, it was the best model. So you don't use a neural network. So I guess my point is that if you have simple variables that do not really vary that much and are easier to predict, then use whatever you have. Don't necessarily use neural networks. And yeah, it should work. It should work well. We should always start with simple stuff that works and then scale up once they start breaking down.
Okay, so we are 5 minutes ahead. Is there a last question? Okay, last question then. Very last question. The mic, yeah. So there is the last question and the very last question.
So Camélia Dadouchi, professor at Polytechnique Montreal. My question will go to Mr. Benomar. And it would be about the risk when you take decisions. All decisions aren't equal. So do you assess for the risk and the imbalance in data sets?
So I'm sorry, if I understood well your question, the question is, do we take into consideration the risk of...
Yeah, you know, if you eat a mushroom, you can just have fun because it's good, or you can die. So
Yes.
do you assess for the risk?
Yes, of course. So in online algorithms, the decisions are compared, are measured by seeing how they perform in face of the worst future possible. So you should make a decision that is good whatever happens in the future. So in fact, you assess a lot for the risk because it's always a worst case. We always give worst case guarantees. So yes, assessing the risk is the very essence of online decision making.
Okay, so thank you very much. Let me again thank them because, believe me, squeezing their passion, all what they do in 10 minutes is not easy. So I would like to thank them for having respected the time, and therefore we can have the coffee break without feeling guilty of being extremely late. Enjoy the break. Please come back on time. Please come back on time. Okay, thank you. So please come back to your seats. We have ahead of us 4 hopefully amazing talks. So again, for the latecomers that I just met, let me repeat what I said in the beginning. This is the Science Week. Some of you even don't know that. They asked me what's going on. This is the Science Week, which is an annual event at UM6P. The goal is to confront the UM6P audience with take some perspective on the world and confront the students with what's going on in terms of science in a general term. And today is dedicated, at least this morning, to the College of Computing. The topic is AI in transition. And when thinking about whom to invite, we decided to invite the young generation of researchers who are making the field of AI. So as you probably know, AI is becoming a buzzword. Everybody talks about AI. Unfortunately, there are a lot of, I would say, silly positions, some nonsense going on, some artificial coaches, some even science fiction on the media. And our goal was to show you what real AI means nowadays. And we have selected 8 researchers because, one, they are Moroccan, and second, they managed to have their papers accepted in one of the best conferences in the field. So this was a clear metric to judge, to measure excellence. In research, excellence is measured by publications, and in machine learning, which is the topic of AI today, the metric is a couple of conferences. One of them is NeurIPS. So I'm going to call the 4 speakers, one after the other, and the goal for them is to squeeze their knowledge in 10 minutes, talking about their personal journey, but also sharing with us their perspective on research and what they are doing. The first is Salem, who actually, and I'm very happy about that, has been giving a lecture at UM6P last week. Is that correct? So I'm very happy that not only he comes to give a talk, but also to give classes to our students. The floor is yours.
Thank you. Oh, I don't see anyone. First of all, it's Salem. Sorry, it's not Salim. But it's okay, no problem. Let's start. So I'm going to talk about my research, which is about uncertainty in machine learning. You probably all know what machine learning is. It's a central field in artificial intelligence, and I'm going to talk about uncertainty, which is an important concept in machine learning. But first, like before me, I will talk about my personal journey that I represent here by an arrow going from left to right, like the arrow of time. And but the arrow of time will start when I got my baccalaureate. Okay, first the years. Yes, you see the colors. So I got my baccalaureate in public school in Lycée Moulay Slimane in Fès. After that, I went to classe préparatoire again in Fès, in public classe préparatoire. After that, I went to École Polytechnique in Paris for 3 years, during which, so back then, like I had one goal in life, which is like to travel and see the world and discover new cultures and things like that. So we had to do internships, and I really wanted to do my internships abroad. So I went like to India for like 2 months, then I went to Singapore for one of the internships. And luckily, like in Singapore, I discovered the research world, and I published my first paper, even though like back then I didn't really know what research is, what publications are. But it was a good experience there in Singapore. Besides, you know, sightseeing and visiting Southeast Asia, like I discovered research, which was really cool. After that, I went to ENS Paris-Saclay to do this master called Mathematics, Vision and Learning, MVA. After which I did an internship in Paris, in AXA. And then I was done with my studies, and I was like, should I go do research or should I go earn money in the industry? And I decided to go earn money in the industry. So I went to Amsterdam and I worked there for a year in booking.com, but I got bored really quickly. You know, like I had some lack of meaning and things like that, and after really 2-3 months of working there, I was really bored, and simultaneously I got this really great opportunity with Yoshua Benjiu, which is one of the leading researchers in AI. He offered me a position as a PhD in Mila, and directly I said yes. So I went to do a 6-year PhD in Mila, during which I also did an internship in Google, and I just finished my PhD 2-3 months ago, and I've been doing mostly nothing since then, but I will start working in like 1 week. I'll be joining TII in Abu Dhabi, working as a senior researcher. Okay, that's it for my personal journey. Let's talk about research, for those who are interested in research. What I'm interested in more generally and very broadly, I'm mostly interested in understanding intelligence. Not only artificial, but also human, animal. How do we reason? How do we make decisions? And I believe that a key to understanding intelligence is to first define it, which is really hard. We don't have a clear definition of intelligence. And maybe just to define it, we might need to replicate it. And if you remember from yesterday's talk from Dan Dennett, he said that the AI revolution is given like one of the first answers to understanding intelligence, because it's one way to replicate intelligence. So this is maybe like the main reason I'm doing research in machine learning. But of course, in research, we always have to divide the concept or the research topic we are interested in into smaller things. We cannot, you know, if you want to build a house, you have to start somewhere. You put a brick, and then you wait for others to put other bricks, then you put another brick, etc. And after a few years, you have a house. So I just focus on one component of intelligence, and we can maybe agree that intelligence is decision-making, and more specifically, decision-making under uncertainty. So that's my current research, working on uncertainty. Uncertainty estimation, how to estimate uncertainty. For example, You know, even human uncertainty, like when you're asked a question, when you are asked to make a prediction, then those predictions will not be 100% sure, but we can estimate the uncertainty that you have in those answers. And estimating uncertainty is essential for decision making, because if you don't know what you don't know, then you won't know where to spend resources to learn more. I repeat this sentence because I'm using don't know a lot, but if you don't know what you don't know, you won't know where to spend resources to learn more things. And this might be reminiscent of reinforcement learning or active learning, where agents need to explore their space, they need to explore their environment, and in order to explore, they have to know which parts of the environment, which parts of the world they don't understand, they don't know how to model, in order to spend more resources exploring that part of the environment. And also one key aspect of my research is probabilistic modeling, because uncertainty is usually codified with probabilities, so we need to estimate probability distributions. So there is this whole field in machine learning and statistics, which is how to represent or how to model probabilities over composite objects, for example. So this is the high level, and I'm going to delve almost without math into more specifics now. So the first part, oh wait, what I'm doing. Okay, uncertainty estimation. As I said, agents need to know the aspects of their world model they are most uncertain about in order to decide where to allocate more resources. You probably know Bayes' rule if you're a scientist, which is, I guess, one of the most important formula in science, and you maybe know Bayes' rule if you were in my class last week. So Bayes' rule tells you, Bayes' rule should have been shown here. Okay. Sorry for the slides, I don't know what's happening. But let's just focus on the line about Bayes' rule. Suppose that you just observe things in your world, in your environments, and you have some model of how the world works. So initially, you just have some prior knowledge that I encode here in this equation on the right by P of model. And Bayes' rule allows you to update this prior belief into what we call a posterior belief that I put here on the left, which is P of model given observations. So this Bayes' rule is very important because that's the rule that encodes how knowledge is updated, how also it's encoded in agent's life. And probabilistic modeling is trying to answer the question of how to model posterior over objects such as world models, objects such as, for example, if you're interested in search problems, like my colleague and friend talked about in the first talk today, when talking about drug discovery, we have search problem, which is searching in a large space, the space of drugs, which is known like to be 10 to the 60, which is a very huge space, or the space of materials. And the search problem can be modeled using probabilistic modeling, like using, we want to, the search space is basically looking for the posterior over the drugs or the posterior over materials. So the research I've done in probabilistic modeling also tries to answer questions about how to search within large spaces. And my contributions are presented here. So for uncertainty estimation, my first contribution proposes an alternative to the Bayes' rule that I presented before. So I slightly lied when I said that's the only way to represent uncertainty, but there are alternative ways, and one of them is this DEUP or DUP that we presented in a journal a few years ago. And for uncertainty estimation, one of the ways machine learning researchers compare or benchmark different uncertainty estimation methods is using reinforcement learning environments. And I've contributed these two sets of reinforcement learning environments, which are called Minigrid and Baby AI, that combine RL and language. And for probabilistic modeling, I was working with many researchers in Mila, and we pioneered this new field called generative flow networks, or GFlow nets, that Lena spoke about about 1 hour ago. And the idea behind these generative flow networks is how to model probabilities over compositional objects. And we do that using a graph that I represent here with the white and the blue nodes. And very simply, you can think of the process of creating a compositional object, such as a molecule, as starting from the empty molecule and then adding some building blocks one after the other, like atoms or molecular fragments. So that's what we represent by this graph here. This graph represents the process of building large objects, such as molecules. And in this GFlowNet Foundations paper, we laid out the foundations behind the GFlowNets, what are the constraints that need to be satisfied in this graph in order to have guarantees of the quality of the generated objects. Then we made some theoretical work linking that to variational inference, and we extended that to continuous domains in the last contribution. And finally, there is this code library called TorchGFN that I've worked on for the past 2 years that you can use. It's open source code if you want to play with GFlowNets. So that's about it for my contributions, and I will take a few minutes to talk about open research problems, my research interests, and things that I will be doing in the next few years, hopefully. First, I want to work on scaling uncertainty estimation methods for efficient active learning. So I talked about uncertainty estimation, but we really want that to work for large models and not just some small tasks. About uncertainty, I didn't talk about the types of uncertainties. It's really important to distinguish between 2 types of uncertainties: the aleatoric uncertainty, the one that is inherent in the world, the one that is inevitable, irreducible. You might think of quantum uncertainty, like radioactive decay or things like that. The uncertainty that's there, it's something that you cannot predict. It's not because we do not have information, it's because the world, the universe apparently is inherently stochastic. And the second type of uncertainty is the epistemic uncertainty, the uncertainty that is due to our lack of knowledge. And this is the uncertainty we are looking for, the one that we are trying to reduce. Third point, I want to use GFlowNets for large language models, which are becoming ubiquitous in today's when we talk about AI. A lot of people think about ChatGPT, Gemini, and things like that. And these large language models, they give you a lot of false information, and they lack reasoning abilities. And GFlowNets have been shown to be able to help in reasoning. And finally, I'd like to work on scaling these GFlowNets for efficient exploration of large search spaces, such as molecules and things like that. And maybe just 30 seconds, if you allow me, Professor Rachid. I want to highlight the importance, like, let's take a step back and, you know, uncertainty is cool, predictions are cool, but there are more important things, and I want to echo what Fouad Lahlou said yesterday when ending his talk. Yes, he mentioned this quote by Rabelais, which is "Science sans conscience n'est que ruine de l'âme," and I want to highlight the importance of knowing why we do all of this. It's cool to advance in AI and say, hey, we have best results, we have beat this benchmark, but we really need to know why we're doing this, and we cannot keep following what American companies funded by billionaires are telling us that this is the right way. We cannot use ChatGPT as a source of information. A lot of people are starting to use ChatGPT like to get information about how the world works. You don't want ChatGPT to gaslight you into thinking that a genocide is okay. So it's really important that people, researchers, engineers understand how the machine learning algorithms work and maybe develop our own algorithms or maybe like influence decision makers when it comes to regulation and things like that. Thank you.
Thank you very much, Salim. Now pronunciation is good? Yeah, I'm extremely happy because this morning we had students coming from SFI, of course, Jdida, Inzgan, and I'm happy to see that there are also students coming from Fès, donc les régions reculées du Maroc sont aussi représentées. I'm extremely happy. Hamza, the floor is yours.
Thank you. Yeah, so it's a great pleasure to be here. I'm Hamza Keurti. and, well, Keurti, but for some reason they wrote it like that. Yeah, great pleasure, and let's get started. Well, I'm going to talk about perception from action, but I'm going to rename it right now as I act, therefore I see. Okay? You'll see why. A few words about me. I started in Morocco with the baccalaureate in Casablanca, and then les classes préparatoires, Casablanca, Rabat. I then went to Centrale Paris. Okay, Centrale Supélec for the younger ones, right? Then you'll see that it's only 2 years, because then I took a gap year, worked in the UK, US as a software engineer, doing optimization, got a patent out of that, and then went to China, also like to travel. Did a Master of Science at Tsinghua University, and this is where I got introduced into computational neuroscience, and I got stung by the curiosity of understanding how our intelligence came to be. And then after that, I got engaged in this joint PhD between the ETH Zurich, right, and the MPI for Intelligent Systems in Tübingen, Germany. My supervisor is Bernard Scholkopf in causality, and well, I don't quite do causality, but yeah. Right, so that's about me, and for my research interests, I'm also curious about our intelligence. Where does it come from? And unlike Salem, I don't think that intelligence is about how we make decisions. I think there's already quite a lot of intelligence before that, right? In perceiving, right? Like you look at the world around you and you have this understanding already of what's going on. And I think that it's interlinked with action, our ability to act in this environment, to intervene on it. I guess this is where causality is. But, and I'm very interested in abstraction, basically to take a very rich amount of information and extract from it simple models. And for that, you have the mathematics of mathematics, which is category theory, and I think there might be a big application for it in this question of perception and action. So yes, mathematics, very beautiful language, and even more beautiful, the mathematics of mathematics. The AI equivalent of perception learning and perception growing acquisition is representation learning. And more precisely, I'm interested in self-supervised representation learning. Not supervised, not just unsupervised, but self-supervised, with traditional problems of representation learning, of disentanglements, representation manifolds, and like group structure and algebraic structure, complying with those structures. I'm also interested in misspecification, precisely model uncertainty estimation under model misspecification. That's something I was interested in, but it's not really my big focus. But very related to what I'm doing is structure misspecification. What happens if you don't think about the algebraic structures of the real world and just train some model to do stuff? So that's about my interests. And let's dive in. So when I say like a perception system, the first thing that might come to your mind is a classifier or a regressor, right? Like some sort of supervised learning model, right? That looks at an image and outputs the label, like a quantity, for example, the pose of the objects, or well, the category here for like, is it a cat, is it a dog, right? This kind of things. The goal then, like through supervised learning, is to find the right map that does exactly that. And you would train this model, fit this model on a big data set of labeled examples. The thing is, these models might have a high accuracy. You'll be happy with your classifier. It says, oh yeah, 99%. But then it doesn't really understand what the world is, right? It doesn't necessarily understand the concepts that are there. It's a mapping, it's a function. And in fact, if you look at existing research, shows that sometimes it's just cheating, right? It's just picking up on some very easy to extract features from those images that's like specific to your distribution in the training data, instead of the actual concept you're interested in. So in this example, you have this data set of cows and camels, and you try to classify between the two. And it so happens that in your training data, well, cows are in green pastures and camels in some deserts. And so what the model does is just pick up on the green background and high accuracy. So green background for the cow, brown background for the camel, and then you bring a new image with like a brown background for the cow, like a cow in the desert, and it fails miserably. So no real understanding of what's going on. And in addition to that, you have like the dimensionality curse, like if you have bigger observation space, or if you have a more complex perception task, then you need much more labels, which is a tedious thing to do. So let's take a step back, or let's focus on what I mean by perception. Like, why is it such a interesting problem that I think is what intelligence is about? I think the first thing to consider to make it clear that it's not trivial, it's not a trivial task, is to look at the observations that you obtain, like the X, right? Like the images, the sound that you have, to look at them as measurements on a physical world that exists outside, right? Like there is a physical world, and then you only capture a measurement, like a projection, right? Of that world, and yeah, that's the image you have. And you don't have access to the W that you see there, like the world outside. You don't have access to that. You don't know the physical process that brought you the image, like the function B, right? And you're stuck with just X. That's the image you have to deal with, and you have to figure out what's going on outside. So I want you to ponder on this, right? Like think about your own perception system, right? And how your brain is inside a black box in the dark, right? And it receives these images. Like this is classic Plateau cave, right? Like shadows on the wall, and you're trying to guess what's going on outside the cave. And this is what your brain is dealing with, and what your artificial intelligence system is dealing with. And then it makes guesses. This is what representation is. This is what perception is. It makes guesses of what's going on outside. So the Z space is your representation space, is your internal model of what's happening outside. And so it's just an attempt to recover the physical world and to maintain, or to, to preserve, oh yeah, it's there, some of the structure. Then, once we have this step, you have the representation, you have the understanding of what's going on, then you can learn tasks. Then you can do your classifier, you can do useful stuff, right? But you do it on top of the representations and not directly on the image, because it offers you some advantages. Like this is a core concept in deep learning, machine learning. If you don't have the right representation, you're doomed, right? Like you have model misspecification, like structure misspecification, and you're making the problem unlearnable. On the other hand, if you have the right structure, if you have the right assumptions for what's going on, then you might get rewarded by generalization, right? Outside of your training data for free. That comes by construction through the structures that you took into account. So more data efficient, you don't need that much data to train on. So how do we learn to perceive? So if it's not supervised learning, like what is it? So let's have a look at the state-of-the-art intelligence perception system. So the benchmarking perception technology, humans, right? So we don't, like the babies, they don't take a deck of cards and like just go through them, memorize, right? Like they learn unsupervised. Like most of the time, they're just observing and exploring their world. And so self-supervised learning or unsupervised learning like brought us some of the biggest representation learning models. You might have heard of principal components analysis, independent components analysis, autoencoders for deep learning. And all of these model different assumptions, but they share the fact that they use the observation itself as a label. So you take the observation, have an intermediate representation, and then the constraint is that from that representation, you should be able to reconstruct what you saw. Right? So this is a good prior to some extent to encode useful information. And the thing is, it also considers all your observation space, it considers them to be IIDs, basically no structure, no relationship between like images that you see, like it's just that they come from a common distribution, right? And all the structure comes from the observation space. Like there is no assumption about what the physical world is, like we're still stuck at the observation layer. Because we use reconstruction, then similarity comes from being closed in the pixel space. It's a good assumption to some extent, but it does not necessarily mean that you have recovered the world outside. So, right, going back to our little baby, they don't learn to perceive in a passive way. They interact with the world, and this is a key assumption. So if you look at developmental psychology, you'll find quotes like, understanding an object is not creating a mental copy of it, but rather internalizing how the object transforms under intervention. So the key transition to have in mind is that we're going from static samples, observations, we're going from that to transformations between observations, right? And so this is where I work. My objective is to rely only on this like observation layer, right? Like observations and the actions that the agent can perform, right? To learn representations of both the states, both the points, the static observations, and the transformations in between the points, such that this recovers the structure of the outside world. We need to have consistency. And this is, okay, bear with me, very simple. You have the world outside, W, you have the observed layer, right? The action that the agent performs is the G that you see, like the arrow in between Ws, right? And your representation is what's happening below, right? And your goal is to transcend the observation layer and make guesses about what's going on outside. And so we use this commutative diagram, very simple thing. Basically, it's saying that if I act in the outside world and then represent, I should have the same thing as if I were to first represent and then imagine or predict the effect of my action on the representation space. Parallelism, right? Like you might have heard of digital twins and so on. Basically, you need consistency between your model and what's happening, what you observe. And we derive from this commutative diagram, we just make it into a neural network form, very simple idea. We have an encoder-decoder, right, between observation and representation space. And then for the action that the agent performs, he knows what action it has performed, and we just map it into a matrix that will transform the vector, representation vector of your image. And this is trained on consistency. Basically, we just pull the yellow dot together, the red dot together, to optimize this system. And then we can recover the structure. Oh, no animation. Okay. And recover the structure for different groups without making assumptions about what's going on outside. The agents can, with just interaction, discover the structure, discover symmetries, discover the group structure of what's going on outside. Even for very complex groups like the SO3. And open problems, so basically this is my line of research, how to maximize what we can get out of interaction alone. If I have an autonomous system, I just give it eyes, like sensor, and the ability to act. What can I get out of it? What can it learn? No assumptions. And so this will drive us closer to an understanding of what our intelligence is, and hopefully derive new algorithms for representation learning, which is useful, as I said, for carrying learning new tasks. And in the long term, I would be very, very, like this was my motivation for starting the PhD, is having sensory prosthetics, to be able to understand what it takes to just plug like a new sensor on a human and have it learn to perceive with it. So that's it. And if you have any questions, you can feel free to contact me on anything. Thank you.
So about questions, again, for those who came late, the plan is after the 4 speakers, we still have 2 to go. If you have questions, you will be able to ask those questions, and we will ask the speakers to come and address your questions. So while Youssef is putting the electronic installation on his ears, remember, the selection criteria for these 8 researchers was clear. It's not because they were my students or my friends or the nephews or my aunt or whatever. These are students who managed to get a paper accepted in one of the best conferences in the field. And you will understand why I'm making that precision in a minute after Youssef comes. So he's putting his... So let me maybe add one point, one remark. You probably all heard about digital twins. In medicine, this is a hot topic. Everybody talks, a lot of people talk about digital twins. And again, we hear a lot of nonsense about the topic. If you want to learn about digital twins, read the papers of Hamza, who just gave you his talk now. So it's not shawada, it's not charabia. These are pure, clear mathematics with the W and the Z, and the W and the Z are the digital twins. Right. Hopefully you remember that these things are actually mathematics and computer science. So I still hope that Youssef is ready, no pressure. Okay, thank you.
Okay. I think it's working. Oh, okay.
So can you, thanks.
Yeah. Okay, I'm very, I think it's not still working. Test. I'm very happy to be here. I think you really have a great campus and great conditions to you to do great research, hopefully, in AI. And one particular topic of AI that I'll be talking about is that of trustworthiness. Okay. Very specifically, trustworthy machine learning. So you might have heard about these existential risks. Last conference went to NeurIPS, and you could meet people in these conferences and have a coffee, and one of the first things they would ask you about is, what's your P-doom? So what's the probability that you think the world is doomed due to AI? Meaning that AI would take over the world. And people have those estimates of P-doom. They could tell you it's 0.3. They believe that there is 30% chance that the world would end because of AI taking over. If you are on Twitter, you'll see like really respected academics try to estimate this quantity. We're not going to try to do this here. We're going to take a much more humble tour into the technicalities of safe, robust, and private algorithms in machine learning. Before that, yeah, I'll talk a bit about myself. So I did Bac Sciences Math in SLA. Then I moved to Rabat, in Moulay Youssef, where I did the Prépa MP. And then I went to École Polytechnique in France, where I majored in mathematics and computer science. And then I started my PhD at EPFL with Professor Gerraoui in 2021. So I'm now a 38 PhD student at EPFL. Okay, so AI is kind of hard to define, but in reality, what people use, most of the algorithms that people use are machine learning algorithms. That's what really enables AI, in my opinion. And it's much easier to define machine learning. So a pretty common way to define what machine learning is essentially to program machines to perform tasks without explicitly telling them how to perform these tasks. For example, facial recognition, instead of having experts design rules saying that if a certain person has certain traits, like on a table, they would write these rules, then you should classify that this person is some name or something like this. Now, we don't need those experts in machine learning. In machine learning, you implicitly tell a machine how to for example, do facial recognition, okay? And now, trustworthiness is a bit trickier. What I think trustworthiness is, or should be, is essentially making sure that the algorithms used for machine learning, those that implicitly program machines, those are not misused. They're not used against how they were originally perceived by their designers. And now trustworthiness, it has many aspects, many sub-communities, and those sub-communities essentially, they define themselves on what particular misuse are we trying to prevent, okay? So I took an example here of what could be some trustworthiness aspects. This is from the EU, because EU, they have in this, recently those regulations, if you heard of GDPR. The US now, also the US Congress is trying to regulate AI, and they're trying to define what trustworthiness is. And here I just took some guidelines, roughly speaking, from the EU ethics guidelines. So the first one, for how they, the first aspect they believe of trustworthiness is lawfulness. They want a trustworthy algorithm to be lawful, meaning to respect the existing regulations, all right? Makes sense? And then you also want it to be ethical, meaning you want it to respect values that are agreed upon in society. And you want it to be robust, meaning you want the algorithm itself not to be manipulable by, let's say, evil people, adversaries, we like to call them technically. Okay, and that's the last part that my research is mostly about. It's really the technical aspects of robustness. Now, as I said, we like to be robust, but then against whom? Who is the adversary? And depending on the adversary, you will have such definition or such objective of trustworthiness. This is, I showed you here like the general life cycle of a machine learning algorithm. So you start from data, train your model, you can deploy it, becomes an API, and then there is an end user actually using this machine learning model. Now the adversary could sneak into any part of this cycle. It could be at the very beginning. They could try to poison the data to make your model classify some specific images as they want, or they can simply want to destroy your classification accuracy, for example. It could happen also near the end. It could happen with some users trying to reconstruct the data, trying to violate the privacy of the data that was used to train models. And this is very dangerous, and we're actually all concerned by such issues. If you're using Android, Google uses your text, your messages to enable more accurate text completion tools. And so we're all actually giving our data without knowing or while knowing. And it's important to know that there is these threats that people can try to reconstruct. Let's say in the very worst case, sometimes some snippets of the text on your mobile. Okay, so those are the main adversaries I'll be focusing on, the ones I actually mentioned. So either the data is poisoned, or the data is not poisoned, and there is an adversary observing some part of your machine learning pipeline and trying to reconstruct the data. Okay. So the latter is what we, to defend against the latter, the most standard notion is called differential privacy, okay? So I didn't write the formal definition, but all you need to know is that differential privacy essentially makes it very hard for an adversary to distinguish the presence of an input, okay? So if you take an input of your algorithm, change it a bit, that the adversary won't really see the difference. So it really makes your algorithm kind of insensitive to to its inputs. Okay, and differential privacy is really deployed, I think, by Google, Facebook, Apple, the US Census trying to aggregate statistics about their population. they use differential privacy. Okay, so it's really widespread. Many people know about it, not just researchers. The other trustworthiness goal we could seek is robustness to poisoning, meaning you have an adversary, they can go to the training data, they can pick a fraction of the data, and they can play with it, okay? And we would like to keep the performance as if there was no poisoning in the data to start with, okay? So we can say I am robust to, say, 5% of poisoning in my data if I preserve, let's say, a 90% accuracy, even if there could be 5% corruption of the data, okay? So those are really the goals we try to achieve. This is my research. And the typical tools we use are pretty simple, meaning you could think of using these in your startup, or you could think of analyzing these for your classes or your research projects. So you can, for example, just inject noise to protect the privacy of your algorithm, okay? So you inject noise, let's say, at the end, and then it's hard for adversary to reconstruct the data, okay? And then the amount of noise you inject really dictates how much privacy you have. Okay, now we have similar approaches for robustness. Essentially, if you're doing a statistic on incomes, you don't want to just take the average of the population's income. You want, for example, to take a median. That's more robust to outliers. And it works very well for very sophisticated algorithms, let's say gradient, stochastic gradient descent. You can, instead of taking an average of gradients, you can try to take some kind of robust estimate, some median-based robust estimate, all right? Those are some objectives. There are many other objectives. There are people who are interested in cryptographic security. They can encrypt, for example, all communications within this machine learning pipeline to make sure that an adversary really just sees noise. But it has its drawbacks, like it can be expensive, but it has this kind of perfect privacy. You have some other notions like adversarial robustness. You have some very different notions of trustworthiness, like fairness. We want our algorithm to be to perform well on every subpopulation. We don't want any minority to be left out by our performance benchmarks. I'm listing here some of my contributions within my group, the group I belong to at EPFL. And essentially, I do theory, but it looks complex, but in reality, it's pretty simple what it is, theory research. What we like to do is we like to prove that our algorithms work in our specific case. And what we really love to do above all is to prove that our theory is tight, meaning I will prove that my algorithm will achieve at least 90% accuracy. That's what I'm going to try to do. And then I'm going to try to prove that, in fact, you cannot really do better than 90% accuracy in some cases. And then your theory is tight. And some of my papers try to convey this kind of messages, and many theory papers try to do this. And it's actually, if you have this mindset, you can enjoy theory research if you're interested in that. Yeah, future research directions. Usually there is a trade-off, a natural trade-off between ensuring good aspects like trustworthiness. When your algorithm is private, you lose in performance. There is a fundamental cost. You cannot evade it. And what we try to do is we try to balance this trade-off. So future directions always include having trustworthiness, but not sacrificing things like computational efficiency. You could think of having a better trade-off by considering weaker adversaries. I told you about an adversary that can corrupt a fraction of the data. You can say that they cannot arbitrarily corrupt the data. You can think of weaker adversaries to have a better trade-off. And finally, you can think of having those trustworthiness notions together. You can have privacy with robustness, with fairness, etc., and study what happens. Can we have a system that really englobes all of these notions together? So that's it for my talk. Yeah.
Thank you, Youssef, for this plea towards the benefits of theory to understand practical problems and practical systems. There is a last speaker, Yassir, standing between now and the lunch, but please use these last 10 minutes to learn even more things about AI today and machine learning. And if you have questions after Yassir's talk, I will try to distribute them as evenly as possible for our 4 stars. So Yassir, the floor is yours. Again, 10 minutes, 1 slide of mathematics maximum, right?
Okay, thank you, Rachid. So, hi everyone. First of all, thank you for the invitation. It's really a pleasure to be here. So today I would like to talk about reinforcement learning, which is the topic that I do my research in. And basically what the title is about is what I call foundations towards deployable reinforcement learning, because one of the main challenges that we have in reinforcement learning is that we're not yet able to deploy it to its full potential. Okay, so about my journey, I started, I guess, as many of us in Morocco. So I did most of my studies, or all of it, in public schools, and then I did prépa in Salem Lahlou, which is in Salah. After that, I went to France, entered NCMAG, which is a school specialized in computer science and applied mathematics. And then I decided by the end of let's say, my second year to do an exchange, where I went to KTH, which is based in Stockholm, Sweden, and I did there a double degree, specializing in control and optimization. After that, I decided to start a PhD, which was with Professor Alexandre Proutière on statistical aspects, let's say, of reinforcement learning. And now I am currently a postdoctoral researcher at MIT under Professor Devavrasha. Okay, so I hope, I know that many of you already know what RL is, but I know that maybe some of you do not know much about it. So I would like to take the time to just explain very briefly what RL is. So what is RL? Basically, reinforcement learning is about learning a optimal sequential behavior by interacting with an environment which typically we don't know much about. So for instance, here you could have a learning agent, it takes an action, and then it interacts with the environment, and then it receives a signal, a reward signal, and at the same time, it ends up in a new state. And the idea is that you carry on this feedback loop so that you maximize your reward over time. And the challenge is that we typically have 2 challenges, actually. So the first one is that the dynamics or the rewards, so by dynamics I mean how the state evolves over time, are typically very complex. And sometimes we might not even know how this evolution happens. And secondly, which is, I guess, something that you might have heard of in many places, I guess, it's the curse of dimensionality, and this is very pronounced in RL because the actions that you might take, there are so many of them, and we typically have very or extremely large state action spaces. And this is a huge challenge in RL. Okay, so regardless of that, RL is still very important and relevant because there are a lot of potential applications for it. For instance, recommender systems, clinical trials, robotics, smart grids, and so on. And I've added a QR code that you can scan to see a list of potential applications of RL. You will have the chance to scan that later on, but just so you know. But it is a very relevant problem, and this learning paradigm has found a lot of interest recently. But regardless of these challenges, I guess you might be wondering, where did RL prove to be successful? Let me just mention a couple of these successes that I hope some of you have already seen before. So the first one, I guess, is AlphaGo. I guess many of you have seen AlphaGo, or at least heard of it, which was developed by DeepMind to solve the strategy game Go. And RL has also been successful in robotics, arm manipulations, flight maneuvers, etc. And perhaps recently, ChatGPT, where it was used to solve the alignment problem, where essentially they used RL so that they can fine-tune the text that you get from large language models, because these texts initially they're not human-like, and so they had to use RL so that they can fine-tune these texts which is generated by large language models. But perhaps one particular, let's say, success that was very interesting to me, and I found it very special, is AlphaGo. And so this happened around, I think, 2016, 2017, as I said, by DeepMind. And since the theme of this week is actually transitions, for me it marks a really big transition in our understanding of AI, because there is before AlphaGo and after AlphaGo. Humanity before AlphaGo believed that there is no algorithm or machine that can beat a human at the game of Go, which is a strategy game. And then AlphaGo came in, and suddenly people started realizing, wait a second, machines can beat humans. So this also is something that I guess Rachid mentioned earlier, that the definition of intelligence is something that is dynamic. So initially, we might not know, we might believe that something can only be done by humans, and then suddenly we see that machines can do it. So for me, this was really a landmark, and it also has sparked a lot of interest in reinforcement learning. But regardless of that, even though there is a lot of successes, there is still an issue with RL. And the real issue is that we cannot still use RL for many other applications. And the reason for that is because the current successes that I have just mentioned are based on things like deep learning. And this is an issue because for safety-critical applications, for instance, autonomous vehicles or something like that, we cannot just use these deep learning-based algorithms without having some safety guarantee on them. And there is a need for a rigorous understanding for these methods. And if we have this rigorous understanding, we might be able to explain why RL works when it works and why it doesn't when it doesn't. And if we can do that, then we could potentially have a lot of use RL in a lot of applications like healthcare, science, and engineering, and many others. Which brings me to my research interests. It's basically just a sentence. What I'm really interested in, at least in my research, is to kind of bridge theory and practice so that we can design learning algorithms in reinforcement learning that are data efficient, so they use data very efficiently. They are reliable, so we can have guarantees on why they work and why they don't. And they're deployable, so we can actually deploy them in real-world applications. And this is very important. So my current research, let me just mention the first one of them, which is very close to my heart since I did my thesis on this, and I worked a lot on topics related to pure exploration. And it has to do with how do you collect data so that you learn a good policy. So in reinforcement learning, as I mentioned, we deal with a feedback loop, which means that we actively select the data that we get. And we need to do that in a smart way. And at this point, we still lack an understanding of how this is done. We have some rough understanding of how we should do it, but we're still not there yet, at least theoretically. But there's active research on this. And it's a very inspiring question, I would say, and that's why I'm really interested about it. And the second one is representation learning in RL. I guess you heard about representation learning from Hamza earlier, which is also an interesting aspect. And we care about it because it can allow us to address the so-called high dimensionality issue in RL. So high dimensionality means that we have far less data than the number of parameters that our models are using. So if you think about deep learning, that's really crazy. The amount of parameters that we use, sometimes it's billions, and we really have very few data, but they still work, which is really amazing. But it also poses the question of why they work. And next, which is more of a fundamental question that has to do with quantifying uncertainty under dynamics. So you've heard a lot of topics about machine learning earlier, where essentially we deal with data a lot, and we deal with this assumption that the data is IID. But the problem is that most of interesting applications, I wouldn't say most, but many of them, they do not respect this assumption that the data is IID, but there is dependencies between the data points that we have. And these dependencies, especially the temporal one, we have to take into account. And this arises naturally in the topic of RL, so we need to understand this at a foundational level. And that's why we also care about this question. And finally, I would also say causal inference, which is something very recent, has to do with COVID, or at least it became kind of interesting because of COVID. And here, the problem is that we need to understand or do prediction under the presence of confounding. By confounding, I mean that there is maybe some hidden factors that explain, for instance, why a certain treatment is better than another one. And this is related to RL because it could be framed as what we call policy evaluation in reinforcement learning. And finally, there is imitation learning, which is also a very cool topic that I'm interested in recently that has to do with how do you learn from expert demonstrations, for instance, in control. Imitation learning is also not very new, but what is new is the nature of data that we have. So before we used to have data which is in the form of signals, now we also have images and we can do things about images. So imagine you have a robot that you want to train and you want to make it so that it can moves like humans. So first you can show your hand move in, it sees your hand move in, so it has as an input an image. It's not really a signal, it's an image, so we have to reason about how we can or deal with this kind of data when we design when we design our learning algorithms from this kind of demonstrations. And perhaps I'll go very briefly about my contributions, which also deals with something very important that I guess Youssef mentioned earlier, which has to do with the theory front of AI, and that's something that I am interested in, or what I work on basically. So my first set of contributions had to do with bandits and Markov decision processes, which are essentially the mathematical framework under which you put reinforcement learning. So everybody that does reinforcement learning has seen Markov decision processes or bandits. And the questions that I've been interested in there or try to contribute into understanding is the fundamental limits of learning, which has to do with how much data you need. So we need to quantify how much data you need, develop mathematical tools for that, and then design algorithms that meet those fundamental limits. And finally, I've also worked on topics related to uncertainty in high-dimensional settings. And much of the work I have done has been published in places like NeurIPS, AI Stats, which, as mentioned earlier, is one of the places where you get to see people that perform this kind of research at the highest level. So it's really important that if you want to do research in this kind of topics, you need to meet people that do research in these topics at the highest level. And these are some of the places where they are. But I think it's also important to go to conferences that are on the side where you can apply this kind of research, and these are more applied topics. So for instance, one of the work that I had was related to an applied problem that was published in IEEE Infocom, where essentially we had a patent that came out of that with some collaborators from Ericsson Research back when I was in Sweden. And then my other topic of interest is learning and control. So this is a very interesting topic because control theory is, it's very fundamental. I mean, a lot of people say that control took us to the moon, and they criticize, people that do machine learning. What did it do so far? Although it's not true because we also have things like AlphaFold that has been mentioned. And there again, I was working on the fundamental limits of learning in dynamical systems. We try to provide sample efficient, excuse the typos, and a recent tutorial came out of this where we wrote a tutorial, where I had a tutorial with a couple of collaborators from the control community, and this was published on control venues like IEEE CDC, which is known in the field, and other control conferences as well. Okay, this brings me to my last slide, where I want to highlight some of the open problems and future directions. So the first one is active learning or online learning in high-dimensional RL. Again, the question of interest is the fundamental limits of learning. We still have a rough understanding of that. Next, there is causal inference. I mentioned that this has to do with clinical trials, for instance. This is, again, an important research topic, and it also has to do with settings where things are not IID. So again, dependencies between data points, this is a fundamental issue. And thirdly, there is also imitation learning. So I already mentioned this. So this is, again, a very hot topic at the moment, and people are trying to understand how to solve this, especially with generative models and so on. And then offline RL. So in offline RL, there is this issue with what we call distribution shift. I'm sorry for the typo. I think things hasn't been updated yet, so sorry about that. But essentially, distribution shift is a real issue because, as I mentioned, we have dynamics, and sometimes we need to deal with problems where we already have data that is available and we need to get or learn from it. And then finally, there is RL with human feedback, which has to do with the so-called alignment in AI, which I mentioned is related to what we called earlier, or mentioned earlier about ChatGPT. And again, this is a very hot topic at the moment, and there's a lot of fundamental questions that has risen there. And just to conclude, there is the QR code if you want to scan and see some of the cool list of applications for RL, which was compiled by Shapa Shibiswari from University of Alberta, and also the lead of the foundations team in Google DeepMind. So I think a lot of these topics are very interesting. I'm very excited about it, and if you guys have any questions, feel free to ask. Thank you very much.
Okay, so I invite the speakers, the 4 speakers, to stay with us for the question session. And let me remind that the goal of the question session is not to talk about you, but to have them talk about something that you might find interesting. Please raise your hands if you have questions. There is a question over there. And then another question all the way on the right. So there is a question here and there. And another one all the way down. Okay, so please, if you can briefly introduce yourself and try to ask a concise question so that we can benefit from their science.
Okay, thank you for the presentation. My name is Ridwan Ibiduni from the School of Collective Intelligence. My question is to Salim. In the node that you display about the neural network, I observed that the first input neuron, and one of the arrows is pointing beyond the hidden neuron, and some of them are pointing back and forth. So I'm confused if it is a densely connected neural network or a sparsely connected neural network. Which of these formation does it use, or it has not been given a name yet?
Are you talking about the graph that I showed in one of the slides? Okay, so that graph is not a neural network. It looks like a neural network, but that graph essentially represents the building process of a complex object. So you start from empty, then you add something, then you add another thing, then you add another thing. You can stop, or you can continue this addition process until you end up with the object that you are satisfied with. So that's why this graph does not have edges between all the nodes. And so this graph is not a neural net, but what we need to learn in order to sample objects that we want is actually a neural network that represents the transition probabilities from one node to the other.
Okay.
Is this okay?
Yeah, I think it is. There's a question all the way down.
Yeah.
On the right.
Thank you very much. My name is Professor Rahil Kamar. I'm from ISESCO. A question to Yassir. Yassir, first of all, very interesting topic that you dealt with. I'm right over here. Very interesting topic, and I think there's a lot of work that needs to be done in this area. My basically question is that the model that you presented for RL, reflective learning, is what we call a unimodal or unidirectional model. Whereas if you look at the human model, it is bidirectional or even sometimes multidirectional and multi-dimensional learning paradigms that we undergo. If you look at the data of autistic children who have learning disability, when we do them neuronal feedback, which is sort of similar to the feedback mechanism that you showed, their learning is multidimensional, and we don't understand that from a simple unimodal learning dimension. So do you think that our computer systems will ever be able to emulate that learning model that humans have? And if so, what are the directions that we need to take to inculcate that sort of a learning model in computational methods?
I'm not sure I understand exactly what you meant by unidirectional and multidirectional.
Yeah, so for your model, the learning and then the reward system and the feedback from the environment. Multidimensional is we learn from, multiple inputs, I'm looking at you and him and here and look, the sound and, the visual context and everything. There is multimodal and multidimensional learning rather than a single dimensional which the computer system incorporates.
Well, actually, that was more of a sketch, but essentially what I called state or action, they can also be multidimensional. Because, for instance, the game of Go, the strategy game Go, the input, or essentially the state, we use essentially the images of the configuration of the game board, so which is multidimensional. So what I put is more of a sketch just to simplify what RL is about. But typically, the state is multidimensional, the action is multidimensional, and indeed the dimensionality is the issue of the problem. So because typically the algorithms will scale exponentially with the dimension, which is not good. And I didn't mention this, but for instance in Go, just to give an example, why this was really a breakthrough is because you can actually compute mathematically how much states you have, and also moves and so on. And at some point in the game, you could even roughly compute the amount of possible moves that you have, and it can be as large as 10 to the power 80, which is roughly the number of atoms in the universe. It's crazy, so if you use an algorithm, which is a brute force algorithm, it will not give you a solution. It will have to run forever, like using dynamic programming. It's not gonna work. So we need some form of understanding of what is the underlying structure to sort of bring this dimensionality down. And they managed to do that using deep learning, which is a great achievement, but we still don't know why it works there and how we can benefit from that success and use it elsewhere.
Okay, thank you. I noticed a couple of people leaving. Please stay until the end so that we can thank our speakers properly. Those who are leaving, I noticed a couple of students. I noted your names. Okay, a couple of more questions. Yes, Ashraf, if you have a mic.
So my name is Ashraf Al-Alari, a professor at the College of Computing.
Get the mic closer.
Yes, so just my question to any of you, how do we get our students to be interested in machine learning where they're actually developing the theory, but not as well keep in mind that this has to be applied at the same time. So if we all apply it, then obviously we're not deep understanding. So how do we tell our students, from your experience, to do both, in a sense?
So I would suggest either Youssef or Hamza to stand up because they didn't pick it.
Test? Okay. Yeah, actually we've been talking about this for the past 2 days. Basically, it is essential when we apply AI that we don't look at it as just like a hammer that you bring a model and you hit with it like whatever problem you have in front of you. There are dangers to doing that. Like you have misspecification, this is what I've talked about in my talk. If you have the wrong representation, if you don't know how the model works, what's happening under the hood, then it won't learn. You're making your model, your task impossible to learn. And so we need people who do theory. We don't have to have everyone do theory, right? Like it's fine to have like different levels of expertise, like some people who are more focused to applications, but we need to have like a sort of community, like collectively that we have, like if I have a model that I go consult to the, like, I don't know, unsupervised learning experts and ask him questions and like get those considerations out of his expertise. So I think we need this kind of interaction between theory and application.
Youssef, you want to add something on this topic?
Yeah, I mostly agree with what Hamza said. I think, I think we need practitioners to develop and deploy reliable systems, and we also need theorists to understand when it works and when it cannot work. So I think we need both. Yeah.
Thank you. One last question. There are many questions all the way there. If there is a mic that could fly there.
Here, please. Hello, everyone.
So maybe you already asked the question. You did?
Okay. Well, if he finishes, I will.
Okay, go ahead.
So my question is to Mr. Yassir.
I want to establish a relationship between supervised learning and reinforcement learning. So my question is there an indicator or a criteria or a systematic way to decide whether for a given problem we will use either supervised learning or reinforcement learning? Because even in reinforcement learning, in some stage, when we have to create our data set and start training the Q function, it's like we are using, in fact, we are using supervised learning. So there is a similarity between the two branches. And also because sometimes, even with labeled data, there is, it turns out that it's more appropriate to go for reinforcement learning. And of course, it also depends on situations. For example, if you want to train Mars rover or a checker program, it is clear that you will use reinforcement learning. But sometimes, in some situations, it is more. It might be confusing to choose whether you will use. You will go for supervised learning or reinforcement learning approach.
Okay.
Thank you.
So after your answer, very last small question, short question. Okay, so please try to make it shorter while he's answering to the previous question. Go ahead.
As you said, like in machine learning, there are like different learning paradigms, starting from supervised learning, unsupervised learning, reinforcement learning. And the difference is really is in the way you obtain the data. So when you have data with labels, the natural go-to is supervised learning. But sometimes I mentioned there is this offline RL, which has to do with data that is already kind of labeled. But the distinguishing feature between the two is essentially having dynamics. So offline RL has to do with taking advantage with the dependency between the data. So there is a causal nature in the data. So data points of the present depends on past data and previous actions taken. Once you have this, you should definitely try to use reinforcement learning models for that. And if you have data which is already labeled, I would say offline RL is the go-to.
Very, very last question. Please make it short.
Okay, thank you. My name is Aurel David Chokonfwe. I'm a PhD student here, and my topic also tackle uncertainty quantification. So it's an honor for me to have you here. My first question will follow the question of the professor, which want to know how we can make students be interested by both sides of AI, theoretical and application. But based on your journey, what's the challenge to go from theoretical AI to experimental and validation, because we know that there are a big gap. And the second question will be addressed especially to Salem. One thing is to design algorithms which better quantify uncertainty and also measure their reliability. But how can we, I think that an open question is also, how can we think about, after the quantification of the uncertainty, how can we design a method to, how can we decide of a threshold which will be independent of our model to decide finally from one sample to another which is really uncertain and what is certain.
Okay, so I suggest that the theory to practice, maybe Youssef or Hamza can say something about this, and then Salem can take the second question. If one of you can talk about it again.
So did I understand correctly? The question from theory to practice is how to apply?
Yes, how to bridge the gap.
Yeah. I think that, especially in the machine learning community, if you look at any of our papers, we usually try to simulate whatever our theory tries to say. And I think that belonging to the community and exchanging with the community, you naturally engage with practitioners. And it's only when collaborating with theorists collaborate with practitioners, that you move forward and you can bridge that kind of gap. So I would say it comes from collaboration and working as a community. Yeah.
Thank you. Salem?
I think your question is how to evaluate uncertainty estimation methods, or how to pick a threshold, like to say whether this prediction is certain or not. So the two questions are related. So for evaluation, usually we use downstream tasks, so tasks where uncertainty is required, and we just measure how many iterations we need in order to achieve a certain level of accuracy. For example, if uncertainty method A requires 100 steps in order to find the optimum of function, and uncertainty method B requires 120 steps to find the optimum of function, then uncertainty method A is better than uncertainty method B. And I'll also like say a word for theory versus practice, and that's not only about machine learning, but very generally, I believe that you should just follow your emotion of pleasure. If you don't find any pleasure in doing theory, don't do theory. If you don't find any pleasure in doing practice, don't do practice. I believe that if you're doing a PhD, you find some pleasure in doing research there, just follow your pleasure emotion, and I'm sure you'll be fine.
So it ends with pleasure. So before closing, a couple of comments, please. The first comment, I said earlier that we didn't want to invite dinosaurs. Please don't get me wrong. There were a lot of species that disappeared and nobody remembers. Dinosaurs, everybody remembers. All the kids know T-Rexes, so we all would like to become dinosaurs. So it was not in the pejorative sense. The computer science revolution and the AI revolution in particular is very different from the industrial revolution. The industrial revolution needed oil fields, needed iron, needed many natural resources. This new revolution needs one natural resource. Artificial intelligence needs natural intelligence. If you look at the big companies today, the people who built these companies are not, they didn't inherit field oils. It's not Dallas or Rockefeller or whatever. These are students. Zuckerberg and Sam Altman and all others, these were students with good formatted brains who created those big companies when they were PhD students or postdocs or whatever. And we are extremely lucky to have the students here today. One of you will one day create a big company or write a great papers. And we are blessed to have these 8 Moroccan students, I'm very happy about that, who accepted to come and give talks here. حمرتوا لنا وجهنا. Let's thank them really warmly. Thank you. So I guess the next step is the lunch break, and the session continues here. There is a special session at the College of Computing with some other bright students will be presenting their talks. And that session, I think, is for special guests only, but maybe some of you will become special guests next year if you behave properly. Thank you very much for your presence.